hear from Jan Kodet about timing and time transfer.
Yeah. So thank you very much, Matt, for the opportunity to talk here. So I'm going to talk about timing and time transfer in SLR. So let's start with the distance measurement of the SLR. So what we are doing is that we are sending the laser pulses through the telescope, which accumulate some delay, and we are time tagging these start epochs within some local time scale, which is running with some distinct offset to some universal time coordinated, so to some universal time scale, which for this purpose we can say here UTC. So when we are receiving the laser pulses, so it also accumulates some delay from the receiving part, and we time tag these incoming pulses also with respect to the same time scale. And here we can formulate the observation equation, so using the time tagging of the stop epochs plus accumulated delay plus this shift to some universal time scale, and the same for the start epoch. And while we are time tagging the epochs to the same local time scale, so the absolute time scale difference to some universal time scale, so actually disappears from the observation technique. So the delays inside the telescope we can measure with some local ground calibration. And at the first glance it seems that for the SLR we do not need any absolute time scale synchronization. But let's look at this more in detail. So the satellites which are moving in on the orbit, so with to something like 8 millimeters per 1 microseconds actually give us the constraint how accurate we need to synchronize our measurements and the telescope to some universal time scale, so which gives us some constraint which is defined nowadays to be 100 nanoseconds. So when we look more deeply into this business, so and consider the absolute accuracy of our time scale or our clocks at the station, so these clocks are also introducing the systematic error into the round trip measurement. And when we consider the longest distance which we are measuring now, it is the moon distance with 2.7 seconds round trip. So we can derive that the clock accuracy on the ground must be 10 to the minus 13 to introduce ranging error below 1 millimeter. So the same we can consider also for jitter of our measurements. So when we use 10 megahertz local oscillator with noise floor minus 155 dB from carrier. So the integrating timing jitter for moon measurements are something like 2.5 picoseconds in timing. So concluding all those thoughts, we can say that for the usual SLR technique, we are happy with some very general disciplined GNSS receiver. So then the question is where we can use clocks and why it is bother. So I will go back to the reference frame. So terrestrial reference frame is our reference for all science and physical realization of a lot of measurements in the ears. And since we cannot realize the terrestrial reference frame on the basis of just one space geodetic instrument, so we must combine 4 space geodetic techniques into this solution. This combination is based on the knowledge of the core station where we measure at regular basis the local tides, but the local tides actually represents just the geometrical distance of the reference point. And there are, and since the reference frame actually is factor of about 5 times worse what is desired, what is wanted by the GCOS definition, 1 millimeter in position and 0.1 millimeter per year in the velocity. So we consider also to using another constraint at the core stations or at the space geodetic. This constraint is the time which can be shared within different space geodetic techniques. So now let's look more in detail. So in the SLR case, so what we need actually for performing or doing time transfer using SLR technique. So in this case, so the previous equation we can reformulate to derive the time difference between two clocks, which is one at the station and the second clock at the some satellite, and we can derive the time difference between clock on the ground and space as to be dependent on the timing of the start epochs on the ground, plus the range measurements with the calibration, and timing bias introduced at the timing on the space segment. So doing this, so we can combine and perform the time transfer between ground and space, and eventually between two clocks on the ground, which can help us for different kind of applications. So for geodesy, it can be physical height determination based on very accurate clocks when they would be available at the stations. Another application is the new realization of the non-geometrical tie, so linking geometry and clock on the stations. So doing this, so we must talk and take this equation. So of course this equation it is simplified equations which takes into account just the station and space segment. There are a lot of corrections which we need to apply to be at very accurate level. So, but when we talk about these biases on the orbit, so the current technology allows us to time take the onboard signals, onboard pulses. So with the system variable biases within 1 picoseconds. So, and with the absolute calibration in the level of the tens of picoseconds, which can also help to disentangle, so decorrelate the orbit and the clock's parameters. The challenge in this case, so the absolute timing synchronization of the satellite of the SLR station is to be able to fire with the laser such that we can use the optical signals on board. The current projects are actually pushing the requirements more to the station requirements, and as an example, so in project ACES, so we need to fire with the laser from the SLR station such that we can hit the open detector window, such that and therefore we need to synchronize the firing epoch with the orbit clocks, such within 100 nanoseconds to be able to see even the laser pulses on board. So another challenge is to keep this transmit the start epoch constant and to track the changes. So this transmit epoch is based actually on two main part of the delays. One part is the delay coming from the start detector, the signal pass to the event timer, and the second part is the timing synchronization of the event timer to a local time scale. Here I put two examples. One actually is the how it should not be for time transfer in SLR. So here we see the timing realization of these PPS pulses. So at the station, so where the epoch is changing rapidly, more than half a nanosecond during a very short period of time. And this timing uncertainty will completely spoil time transfer capability of the SLR. So here is the improved electronics, so which introduce almost no signature, and it is influenced by just a white phase noise. So when we move from the timing from the start detector, so we must also talk about the calibration of the range measurements. So here we plot actually the ranging to an external target at wet cell. So and what we see here is the small variations in the level of a few millimeters, and this is still always open question. Is it the real variation due to some distance changes of the detector, or is it something, some error which we are introducing in the system? So, but this, when this is error, so then it would directly go into this time difference comparison, and therefore we must always take care also about this internal or external calibration, and put it always into the question whether we are doing the job correctly, because it reflects in this equation directly. So here I put where the technology is lying for SLR technology. So it is for room or laboratory experiment where we range just to a constant distance target. Here we see during several hours experiment, so the data are very nicely stable. So and when we perform some statistical evaluation, so we can trust these data down to 40 femtoseconds for averaging time up to hours, which would actually enable to make time comparison of some, for instance, optical clocks at the level 10 to the minus 16, so which is very good. When we consider something like where the theoretical limit with the state-of-the-art SLR technology is lying, so I plot here some lines. So these data were derived for 100 Hertz experiment. So when we are increasing also the repetition rate of the laser, so this statistical uncertainty drops down, and we can average much faster. So which is depicted here with this curve, and when we use very good detectors providing 15 to 25 picoseconds RMS, so we can reach even lower limits. So this is everything nice. So, but it is a laboratory experiment. So here I would like to highlight very successful experiments derived by the French colleagues within T2L2 experiments. They provide a lot of measurements and a lot of experiments. Here I would like to highlight the comparison between T2L2, laser time transfer, and GNNS comparison. They were able to track all the unknown biases down to 100 picoseconds, and they have very nice time comparison within 100 picoseconds between GPS and T2L2 between Graz and Hermsmoor station. So this is actually where we should go with the technology and with the future work. So, and put into the question whether we can knock this 100 picoseconds even to the lower levels. So at the end, I would like to here acknowledge a new research unit which was submitted by to 22 colleagues. We prepared with the head of this research unit, Ulrich Schreiber, so we prepared a working program or a research unit, call it clock methodology and novel approach to time in geodesy. The main goal is to introduce accurate clocks and to introduce clock ties as a new tool to probe the space geodetic techniques. The group has 22 participants. We submitted 10 separate projects and applied for 12 PhD positions. So, and here I would like to highlight the actually heart of the entire project submission is to operate 2 optical clocks. One strontium optical clocks will be operated at in Wetzel Observatory. So, and the second optical clocks we would like to provide to Potsdam SLR Observatory, but because we don't have access to another optical clocks in Wetzel, we will use strontium clocks from Stefan Schiller group. In Potsdam, we will use optical fiber connecting Braunschweig and where the enemy of the Germany is located. They operate also strontium clocks, and they will provide through fiber link where these strontium clocks to Potsdam Observatory. Here are listed expected uncertainties, so we would like to do the optical time transfers through the ACES. So here I would like to highlight, so ACES is still alive, so we had a new date for launch, which was shifted to 2025. And within this optical time transfer over ACES, we would like to reach in total 5 picosecond uncertainty for optical time transfer, which we will use for demonstration to for height level definition with uncertainty at the level 0.3 meters, and with future actually work to improve the clock ties. So now, this is everything from me.
Wonderful. Thank you, Jan. Thank you very much. Thank you. Would anyone like to ask a question, what they've just seen? And I did say, Pierre, any thoughts on anything you want to add on from the T2L2 perspective? What are the challenges in timing?
Thank you. Yes, thank you very much. Like that? Yes. Thank you very much, Jan, for your presentations, and also Ivan also. For me, introducing time in geodesy is very important for the future. But of course, it is not possible to have a strontium clock in every stations, every SLR stations. So we have to deal with existing equipment. And for example, because you talk about that, there are some GNSS driver of clocks which are used to construct UTC realizations inside the observatory. But what we discover with T2L2 is the fact that, generally speaking, this system is not calibrated in terms of time. And so we found that a lot of SLR stations, so I remember that T2L2 existed for 10 years, between 2008 and 2018. So, and during this period of time, around 30 SLR stations was able to fire JSON2 and then T2L2. And during this time, we analyzed all this measurement and considered that a lot of stations were shifted for more than 200 nanoseconds from the UTC, statistically. And this time bias was always positive due to the fact that the longer of the cables inside each station were of course very long. So some stations participated in this project, one in introducing a measure which is better than the rubidium, of course, and two, in making the effort to make and to provide a new way to make the calibration of the system. And of course, if we will be able to make this calibration effort in terms of time, I think it's a great opportunity for further geodesy, and of course to improve also stability, bias, and so on, which we need now in geodesy. Thank you.
Yep. Thanks for the comment.
Thank you. Yeah, thank you. Right, we'll move on. Thank you, Jan.